Okay, welcome everyone. So we're at my house and we're gonna do the Sigma Lectures Weekly Steels Yap. So basically there's a link tree here, and you go linktree or linktr.ee/Sigma Lectures. You can scroll down. There's all my notes for various courses and stuff. But you know, there's like the Steels one. You click that. Make sure it's working. Let's check the recording is working. Yeah. There's a few documents here you want to pay attention to. So yeah, basically I'm gonna be going off Steels Yap week 1. The rest haven't been made yet, pretty much. There's also my cheat sheet from back when I did it, and yeah, hopefully find those documents useful. My internet's kind of being shit right now. There's also this, which I actually stole from work, but you guys might find this interesting. I didn't really talk about this in the crash course. There is just kind of like an answers sheet for any prefabricated steel section. This is for non-open sections, so there's going to be hollow sections, which are like hollow boxes or like hollow circles. That's a different document. You can probably find it online somewhere. But this is a really, really useful document. So once that loads or whatever. And then there's also the One Steel catalog, which we'll talk about in a second. But so the first week, we're going to talk about structural design in general. That's the first like overarching thing, which includes the capacity equation, load combinations, and we'll talk about material strength. And that's like just the preface for the course. That's the first half of the first week. And then the rest of the first week, you'll be doing tension design, which I want to focus more on in this YAP. And like we'll even run through an example and stuff like that. So you can see kind of how the whole thing meshes together. So, first things first, if this comes up on my screen. So, this is the capacity equation. So some of you guys, actually everyone in this room has done concrete before. But for the people watching this video, this might be your first design course, because in second year you did solid mechanics, you've done like engineering mechanics, you did structural analysis maybe. These courses don't really show you what like a design engineer does in like a workplace and stuff. Design engineers have to satisfy this equation essentially. It's saying that the external forces have to be less than or equal to basically how strong a structure is, right? I'm gonna do it like this. And this is your structures strength, essentially, right? So, you guys have heard this analogy before, I apologize. But imagine there's 3 tradies on some scaffolding. So the 3 tradies are essentially your external forces. They're the weights that's gonna push down your structure, and your scaffolding, whatever, is gonna be a structure. And you need to know how strong that's gonna be based on like how big it is and the material strength of it. So the thing is about this equation is, if we have the tradies, let's say they're 100 kilos each, and there's 3 of them, so like 300 kilos of external load, and then your structure, it can take on 300 kilos of load, right? Do you guys see a problem with this? What's the problem with this?
What if somebody drank like one entire solo?
They drank a solo, so they're heavier than 100 kilos, right?
Yeah, like
So then the structure just breaks, doesn't it? What's another thing that can happen?
You could have 2 solos.
2 solos. True. What's another thing that can happen, but more for the structures side?
Like there's
Don't say 3 solos.
there's like errors, manufacturing errors.
Manufacturing errors. Exactly right. Yeah, someone could have built the scaffolding wrong. They could have lost the bolt like Josh did when building my table just now. Or like, no, I'm kidding. No, sorry.
oh, they could have done 4 solos.
4 solos. Yeah. Fuck. This is the kind of things that engineers have to think
The
about.
table also had a solo.
Exactly. There's already a solo on scaffolding. Anyway, don't say 5 solos, lucky, alright? If we hand down. Anyway, point is, things can vary, and so we have to account for the worst case scenario. So, this little star next to your R, so R is a generic action, right? We could be talking about tension, compression, shear, bending moment, everything. So the star is just indicating that you've factored it. So factoring means that you exaggerate your load, your external load, by some amount. Let's say by 30%. Okay. And so the tradies, instead of pretending that 100 kilos, would pretend that they're 130 kilos, right? That's essentially what factoring does. So the other thing is this phi value. So in Greek, this is like a phi letter. This is the capacity reduction factor. So this does essentially the same concept, but on the other side. So this is this is accounting for the structure and like the materials, like the steel, exactly, like pretty much. So yeah, this will be something in the ballpark of 90%. So we pretend that our structure, like in this case our scaffolding, is only 90% as strong as it truly is, right? Because we're accounting for those manufacturing errors, all that stuff, missing bolts, whatever. So that's essentially the gist of it. So as I mentioned, the factored external action could apply to tension, compression, moment, shear. So you're going to see different letters instead of R representing this. Okay, the next thing is capacity reduction factor. Oh, sorry, it's 0.9. For most of the course, it's going to be 0.9, but for a couple of the weeks, it's not going to be 0.9, so don't get caught off guard by that. It's a lot easier to calculate than how you do it for concrete, essentially. So RU is basically going to take us the longest to do because it's based on the Australian standards. So there's a document called AS 4100, and it tells you the year that it was updated. So AS 4100 2020, right, is the most recent edition of how to calculate steel members' strengths. And I will release a video on how to access this because my old video, I've been told, is outdated, so you can't actually use that method anymore. But yeah, there's a way to get these standards. They have like a high like security on like the PDF file, so you can like on the PDF. So you can like, yeah, it's really aids essentially. You have to refresh the license every 30 days or something like that. But on the load side, where this comes from is another document which is also Australian standards or New Zealand standards as well. 1170. There's 0, and then there's 1170.1 as well. So this is generic regardless of material. So this is what you guys would have used for concrete pretty much as well. And if you decide to do like timbers or something, same concept. These are just loading action combinations for Australia and New Zealand. That's what they use. Any questions so far? Okay, epic. So basically, from AS 4100, your first week's content is going to be like tension. Your second and third week compression. Your fourth and fifth week is going to be moment. I think week 7 might be shear. So yeah, the course is just broken up into methods of calculating the right-hand side of this equation, essentially, like the capacity. That's how the course works. But let's talk about the left-hand side again. When I say left-hand side, I'm talking about left-hand side here. So basically in steels, we don't talk about anything to do with serviceability in this course, I think. So serviceability is about like the deflection of a structure, how much it's going to sag. So if there's like a ceiling or something, this is the deflection. How much it's going to sag over time, stuff like that. We don't really, like we actually do care about this a lot in real life, but it's just not included in this course. We care more about the strength limit state. And the strength limit state, does anyone want to have a crack at explaining what this design's for?
It's, is it the factored load of how much we can consider it to be its max capacity?
Kind of, but like, say you were explaining this to not an engineer or something, like, what's essentially what this point of
basically
this
how much you can hold.
Is a word I'm looking for.
Right?
It's like ultimate, right? It's ultimate point or whatever. It's like, yeah, exactly that. But yeah, so there's different combinations to account for the worst case scenario. That's another way, of saying it, right? The first one is this. Okay, I should probably explain G and Q. So G stands for dead loads. So I'm just like mixing colors like crazy. There's no semblance of one of them. So dead loads and live loads are different because of the time they're applied on a building, essentially. So dead loads are things which are going to be there for something like 100 years plus, you're expecting them to be. Live loads could be there for a day, they could be there for 50 days, whatever, a year even would count as a live load. So what's an example you see in this room of like a dead load?
Chair.
The bench.
Maybe not the chair. Yeah, exactly, that's right. So that, see the word, see it. That kind of bench is like a part of the wall, and so that's a dead load because we can't move it, right? This chair is a live load though because we'll move around. And people count as live loads. This television counts as a live load because I could decide to just move it somewhere else, right? So things which are permanently fixed in place are dead loads essentially, right? And so we have different considerations on how we deal with them. So we take the worst case scenario, we're going to take the maximum of all these cases. We calculate 1.35G, 1.2G, and 1.5Q, summed up. 0.9G and wind, this is wind loading. That's usually, actually, which direction would you assume wind loads come from? Because we didn't really talk about it. Lateral, right? And that's different to gravity loads. Dead and live loads, yeah, exactly. Yeah, so wind loads actually do come into steels. Because concrete, we didn't talk about wind loads before. So we'll see this in the question below. And then here we have dead, wind, and then here's something called a combo factor. It's in 1170.1. And it's 0.4 for most cases, except 0.6 for storage buildings, because storage buildings are expected to hold like more shit, basically. So yeah, that's the value that we use for that kind of building. So yeah, I'm just gonna skip over this stuff. This is just for context. Units, notation, things like that are gonna be here. Things are unfactored unless they have a star next to them, in terms of like external loads. And if you do have a star, it will be factored. Okay, material strength. So steel has like a metallic lattice essentially, right? So it's a bunch of positively charged ions or something like that, and you have like your sea of electrons, all that stuff. And essentially, it's ductile, steel's ductile, and it's really strong. It has like a high stiffness, high elastic modulus, and this is going to play into how we consider it. And the other thing to note is on a material curve. Okay, essentially, regardless of if you go into, let's call that tension, and then this one's compression. Regardless of tension or compression, steel will have uniform properties, approximately, because of the way that it behaves, like on a molecular level, right? So you guys went to the crash course. Can you tell me a little bit about this, Fy and Fu?
Fy is the point at which it's being strained, and the stress that it's experiencing is that it starts to yield, which means it's going to a plastic state.
Yeah, exactly. Yeah, so, yeah, sorry.
And then the ultimate
Fuck you.
The ultimate strength is where it completely breaks.
Yeah, and we only use the Fu. We only use Fu for the tension calculations, fast fracture specifically, right? So Fy. Okay, actually, let's zoom in a little. Essentially, here's the elastic region of our steel, and it follows this straight slope, and it behaves linearly, right? It's got an elastic modulus, and we actually know the elastic modulus is 20,200 GPa, right? As you strain it more, so you pull it apart more and more, it reaches this plastic plateau, right, where it starts behaving like, I don't have my Play-Doh on me, but like I'm stretching it, and it basically behaves like Play-Doh, where it will just start necking, and yeah, it will behave plastically. And then at a certain point, it's going to do strain hardening, which is like, it gains a little bit more strength because the dislocations from the yielding. So you're pulling this apart, the dislocations start impeding on each other, and it actually gives itself more resistance than even its yield strength. Does that make sense? This is something that happens in tension. Yeah. Okay. Okay. So, the other thing about material strength is it depends on steel grade and thickness. So there's going to be two steel grades. Actually, wait. Also, this is given in the question. The steel grades will always kind of be specified. So you'll either be working with 300 plus, grade 350, or specifically for hollow sections, there's also ones which start with C, but it will always say it in the question. So that's how you're going to find your values for like FY, FU, all that stuff, right? And there's going to be a table for it. The table looks like this. And you just find the appropriate part in the table.
Do they ever troll and ask you to find it backwards?
Sir?
Do they ever troll and ask you to find it backwards?
Nah, I don't think I've ever seen that. No, because the steel grade will kind of have like a cascading effect, I think, on like the rest of the questions, so it would just be too fucking cooked to it. Because like on one steel, like I think certain properties will vary based on the steel grade, not just FY and FU, like fucking heaps of things will change. So there's too many variables if they ever do that. The first one we're going to talk about is tension design. So like this looks very familiar to what we saw before we saw this in terms of R, RU and R star. So now it's going to be NT. NT stands for tension, yeah? And so NT star is, actually, well, someone tell me what this is.
NT star is the tension forces that are factored in the
Yep. Factored tension forces. And is it external or internal?
External.
Very good. What's phi?
Phi is the capacity reduction factor, which is 0.9.
Yes. It's 0.9 in tension, and you're going to find it's 0.9 in compression, it's 0.9 in flexure, and there might be something different for shear, but like it's going to be 0.9 most of the time. Okay, NT. Now this is going to be one of two things, right? The first type of failure, actually you guys were at the crash course. Do you remember the first type of failure for tension?
Sorry?
What's the first type of capacity we should check for?
Yield.
Very good. So yield failure capacity. What's the other one?
Twisting.
Twisting.
No?
Nah.
Oh, fast fracture.
Fast fracture. Very
Yeah, exactly.
You piece of
good. that's what you said, right?
Oh, God.
Very good. Anyway, so we'll see what those are below. But okay, say we take the we do all these load combinations: 1.35G, 1.2G plus 1.5Q, etc. Do we take the max or the minimum for this?
For the left half?
Left, yeah, for left hand side.
The max.
Very good. What about the right hand side?
Minimum.
Why is that?
Because you want to find the capacity of it, and you want to always take the smaller one because then you're designing for the worst case.
Yeah, it's gonna break first, right?
Yeah.
Yeah, exactly. Great. And so the first mode of failure we're gonna look at is yield. This one's relatively easy, and they teach it to you first in this course. It's so fucking laggy. Sorry. Keep on doing this.
Don't edit this out.
Hmm?
Don't edit it out.
Yeah, I'll just make everyone watch. Actually, might just.
Music during it.
Yeah, I think I will actually. Okay, so here's what it looks like. Yield failure. So do you see what I've drawn here? It's like an I-beam or an I-column could be, and it's being pulled apart, right? So the external forces, tension's a two-force action, and then we care about the gross cross-sectional area, right? Because I know I said this in the YAP, but what's the equation for stress in general?
Force over area.
Exactly, right? And in the Australian standards, full stop, we care about forces or sometimes moments
Stress
for
times
flexure.
area.
Exactly. So we rearrange this for force. So that's going to be let's do area times stress, right? So what is our maximum stress which is going to be allowable for yield?
What do you mean? Like a number?
Yeah. What value will they gonna do they care about here for yield failure?
NG.
Hmm?
NG.
NT, but NT is this, right? That's a force.
Oh,
So what do they care about for stress?
area.
That's area. That's going to be AG.
FY.
Exactly.
What?
Are you familiar with the idea that like F is a form of stress? As in like, so if you have a material curve like we see here, right? Your stress can be any variable along this y-axis, right? Any variable number, but we care about this point because that's what the material can handle, right? That level of stress is what the material can handle, and so that's why we take Fy. Does that make sense too? Yep, I believe you when you nod. So that's the necking behavior that I was talking about. It's like where the cross section gets stretched thin because I don't know why. Like it just gets stretched thinner because of how the particles move, and yeah, it's like ductile, so it'll kind of melt almost. It'll have this kind of melting shape.
Wait, can I ask a stupid question?
No such
Yeah,
thing,
that's my filter.
unless you ask it. No, sorry. No, go on.
So why do you have to do Fy instead of Fu? Why?
So essentially, Fy is to do with yield failure, and
Right.
yield. Basically, once we've reached this point, we consider the steel to have failed, right?
Yeah.
You look comfy.
But like, it's like the point when it starts stretching, right?
Yes, so that's already considered failed.
Why? Like it's still like.
There's still more to go. It's because it's not structurally safe anymore, because it's going to kind of have this cascading effect.
So what about
Right.
like the exponential decrease? Like, why can't you consider that?
Wait, what, sir?
Like, why
You know
can't,
the exponential increase?
like, why can't you just like consider like I don't know, like why can't you just keep it there even if it's a little bit stretched? Like everyone's
Because
perfect, you know.
I think it's because that once it's already stretched, once it's yielded, you'll never go back to its original strength.
Yeah, it's plastic.
Oh.
So like if you put on a load that caused it to yield, then it will yield like way more than it first did, because it's not as strong as it was originally.
Yeah, and like once it's yielded again, I think there's cases where you can replace it and stuff like that, but like it's structurally not sound anymore.
Okay.
Yeah.
It's just so rude.
But then the FU case is essentially where it does this step so quick it like kind of skips it, and that's the fast fracture thing, right?
Oh, okay.
Yeah, it's like a brittle motor failure.
Oh, like fast fracture use FU?
Yes.
Oh wow.
Okay. Okay. So fast fracture, let's talk about that actually. It does use FU here, but it has a smaller section than the AG case, the gross area, and it's because of okay. So we have this 0.85 value for like kind of a brittle reduction factor, and then there's also something called correction factor, which we'll talk about. But let's focus on that area, right? So, if we have two failure modes like this, what's the difference between these two failure modes?
One of them is breaking like more towards the center.
Firstly, what are these holes from?
The tension.
Termites.
Yeah, termites. No, what are these holes from?
It's from the tension.
But
The yield.
like they didn't just spawn out of nowhere. There was a reason.
They were like drilled through.
Yeah, the bolts.
Yeah.
The bolts. Right. And so bolts will reduce the cross-sectional area,
Yeah.
making it weaker, right?
Okay, yeah.
But then if you're stretching it, has to travel a longer way.
Yes. So I'll talk about that in a sec. So before we were talking about the gross area, so we don't actually care about like the bolts, like causing holes, right? But now we're talking about the net area, which is the area minus the bolt, kind of like the areas that the bolts will reduce off of it, right? But we have two failure modes that you can see here. So one is unstaggered holes, and the second one is staggered holes, right? So like you said, Josh, what are some features of the staggered holes?
The fact that they have to travel further. Like,
But does that increase or decrease the cross-sectional area?
Increase.
decreases.
It decreases the cross-sectional area.
Huh?
No, as in like that's what you're saying, right?
Yeah.
But if I'm like visually looking at it, it looks like it's increasing it, right?
Yeah, it's increased. 'Cause
Yeah,
it's
yeah, exactly.
Diagonal.
Exactly.
Yeah.
So that's more surface area
Yeah.
than the one on the left.
Yeah.
However, the holes reduce the cross section area, doesn't they?
Oh.
The holes do, but then the
Diagonals
Yeah.
increase it, don't they?
but also we have to think about the plane that it's being stretched at, right?
Yep.
So this is it's
Yeah, why don't you
reduced
just
on, like,
read the
this.
universe while you're at it?
She's good.
it's
Hang
reduced on this axis.
Yep.
But then we're stretching it on this axis. Does that really?
Oh, it will still count.
Okay.
It still counts as an increase in cross section area. However, which one's bigger? Which one's got a net bigger cross section area?
The increase part.
Sorry, as in like between failure mode 1 and 2.
Oh, failure mode 2.
In this drawing, maybe,
But in
But
reality,
in general-
one.
but you have to check for both.
Oh.
Because the holes will reduce the cross section area, but the diagonalness will increase the cross section area. So it depends on the ratios.
Okay.
Exactly. Exactly. So, yeah, as you can see, here's the first failure mode, and this is the equation we have for it, right? It's the gross area minus, this is the sum of the whole diameter times the thickness. So why haven't I done like pi on 4 d squared or something like that?
Because it's like in year 1 when you go like draw the cross section of this shape and it's like a rectangle.
Yes, pretty much.
Wait, is D the diameter of the hole?
Yes.
Um,
So why have I not done like pi on 4 d
because
squared?
it's not actually a circle. It's a like the distance from one half of the beam to the other.
No, you're
It's
right.
actually a rectangle.
It's that, isn't it?
Yeah.
So the whole diameter is that, right?
Mm.
And then we actually consider the thickness of the web in this
Yes.
case, but it can be on the flange. That's a good time to maybe talk about that. So just terminology that we're going to be talking about. So if this is an I-beam, these are flanges, and this is the web, and it's based on this kind of like horizontal dimension, and the web's that one, right? So it's about like the width. So the part with the smaller width is the web, and oh, it's working. Oh my god, it's beautiful. Okay. Thank you. Alright, Lucky, shut up. Alright, let's keep going. Failure mode 2, staggered holes. So, here's the formula for the staggered holes version, right? So we take the gross area like we did before, except like we were talking about, right? We have to subtract each hole, right? Like before, but we add on the diagonal zigzag. So there's going to be terms that we're going to use here. There's the gauge distance and the pitch distance, right? So pitch is going to be laterally, and gauge is going to be vertically, okay? That's the difference. And so we just chuck it in this formula, you don't have to think too hard. All you need to do is measure the pitch and the gauge distance. You chuck it in and you'll get the net area, right? So from the net area, are we going to take the minimum or the maximum for our capacity?
The
It's capacity. Exactly. Right? Because we want the worst case.
yes.
Exactly.
When the
Right.
stress is higher when the wait. The force and stress is higher when the area is smaller.
Yes, that's right. Yeah. Anyway, so we take that. So we're gonna like in this case we have two failure modes to compare, right? Failure mode 1, failure mode 2, right? And that was just for AN, right? And then we also have AG, right? And we multiply that by FY here, right? And then between these we take the minimum. So this is the capacity, right? Capacity, and then we compare that's fast fracture up the top. At the bottom is yield. So we're gonna just keep comparing shit essentially. See how it works? Yeah. Correction factor is the last thing I want to talk about. So correction factor is like an offset value essentially for when tension's running through our section, but it doesn't run through the middle, right? So for example, where's the force? If I was to average out the forces of tension, if it's being pulled, right? Where would the force be applied? In this section. Right in the middle, right? So in this case, KT is equal to 1, right? But what if I had a different type of section? So you guys might have seen this before. This is an equal angle, EA. In this case, is the force going to be applied in the middle?
No.
Why not?
Can you please repeat the question?
So if we have a bunch of like mini arrows from like the stresses
Oh,
of
like
tension
that.
being pulled, right? Is the force going to be applied at the centroid, the geometric centroid?
Yes.
Is it?
No.
It's going to be applied throughout the entire.
So where would the average of the force be? You know,
The neutral axis.
neutral axis to do with bending, right?
Oh,
In
yeah.
the centroid.
But it can't be pulled in the air, through the air, right?
In
So
the
so
corner.
if that's the centroid, is that where the forces are going to be?
No,
pulled?
it's in the corner.
It's going to be in the corner or something, right? So that offset is going to cause the correction factor KT to be non-1. Yeah, exactly. So it's 1 if it's symmetrical and it's in the middle.
And then
It's non-1. Yeah, it's less than 1 if it's not pulled in the middle. So there's a bunch of rules for it. That's going to be found here. This is from lecture slides, but like yeah, you can just look through the table.
Pretty interesting.
Yeah. So this is there's some pretty common ones. Okay. You'll see like
Oh.
EAs and UAs be used a lot, and PFCs. But anyway, you got used to them. Alright, so we'll talk about initial sizing in the question, but essentially we have to kind of guess and iterate on what our best starting section is going to be, and then we're going to see like okay, so basically there's going to be a set amount of external load, right? And then we're going to have to try to pick the best section to take on that load from one steel. That's kind of going to be the question that we're going to be given. And if it's too much, right? What's the problem of if we choose a section that's too big for our forces in real life?
Too much resource waste.
Exactly. Yeah, you're going to be wasting money. You're going to be wasting carbon emissions and shit if you care about that. I pointed out extra. No. And then what's the problem if it's too small? The section we chose is too small.
And it can break.
It's not safe, right? Okay. With that said, let's look at the question. Pull my notes. Fuck.
Henry, I think I know why it's so crunchy.
What?
I think when you're connected to the hotspot, it auto goes to low data mode.
It's okay for now, but I think this is a bit of an improvement from my one, still. But yeah, whatever. It is what it is. Okay, so here's a question. Select the minimum mass PFC for a diagonal member of the truss shown in Figure 1, and there's going to be permanent, imposed, and win actions. All right. So if you were given this question, where would you start?
Figure out the loads, the live loads.
Yes.
And the dead loads.
Yeah.
Figure out which combo.
So you're not given like in Ench 1300, you'd be given like a simplified truss diagram with
Yes,
forces
so
on
then
it.
You'd have to solve for the.
Exactly. But in this case, we're given it somewhere else.
It's in the question.
Yeah, exactly. That's right. So it's just straight up on here.
NQ, that stuff, right?
Yeah, exactly. So what does NG plus 80 kilonewtons mean? Can someone translate that into like a English sentence?
Is that
Is that the dead loads?
yeah? So you times that by 80.
No, it's the dead loads, but you just add it by 80. You just add 80 kilonewtons onto dead.
No, it's positive. It's facing downwards since we know that the frame of reference would be.
Or does it mean that it is positive? Does it just mean that the dead loads is positive 80 kilonewtons?
No.
Tension.
Exactly.
Oh.
No.
So tension's positive.
Oh.
Okay, what about
It's right underneath.
what about NQ? What about NQ?
NQ is tension in live loads.
Yeah.
Exactly, right? And it's bigger. What about this one? What does this shit mean?
Both in.
It's wind.
But what about the right hand side here? Yeah.
It puts everything in tension
What?
and compression.
Wait, what's the
Do you-
minus?
What does this shit mean?
Plus minus.
Minus plus.
Sorry, my bad.
Oh.
Minus
Because
plus,
the
but you have to
wind
check for
goes-
both anyway. So
Because the wind goes either direction.
yeah, no, that's literally why.
Yeah, I know.
Okay. So it will literally be pushing and pulling, yeah, right? So you're accounting for both directions. Okay, what else can we see in this question? Right. Firstly, this part, hint, member must be designed for both tension and compression. We only care about the tension one because we haven't talked about compression yet, so we're just going to do tension this week, right? Okay, we're back. Okay, but what does the question mean?
What
Like-
do you mean by what does it mean?
Like, what is the question fucking asking us to do?
It's asking us to select the minimum mass PFC for the diagonal member of the truss.
So what does that mean?
Shown in figure 1. So it's basically telling you, like design the truss like with the dimensions that it would hold that load.
Yes. So what's PFC? That's a trick question. You haven't seen it yet.
Yeah.
So parallel flange
I
channel.
was gonna make something up.
Parallel flange channel.
Hi.
It looks like that. So C-shaped. These are pretty common for truss members, right?
Yeah.
For beams, beams when we do flexural design are gonna mostly look like that.
Okay.
Which
Um,
ones can you do?
But yeah.
Um,
So minimum mass just means the smallest one that satisfies.
Yeah.
Right. Yeah. Okay. So step 1, we're gonna do the loads. So before we saw the numbers, but what are actually?
G was 80.
Oh, nice! You got a good memory.
Q I think was 160,
Very good.
and wing was 140 plus minus.
Damn.
It's in 0.4.
Very
Those
good.
are the two.
Yeah.
It's
So
0.6 for this question.
Why?
Yeah, but
it is. But it doesn't say why. But it's a storage building. I don't know why it doesn't say in the question.
Or is it a storage?
Oh wait, storage buildings is 0.4, right?
No, storage building.
it's bigger.
It says
It's bigger.
0.6 on his notes.
Yeah.
Oh.
I don't know why it doesn't
Obviously
say that. But Prash did this and it's working out. So we're gonna put in
But
0.6.
0.4 for usual. So
Yeah,
if it
yeah.
did, since it didn't say it in this one,
Yeah.
we would assume actually it would be 0.4. But considering you're saying it's a
Yeah,
storage
yeah,
building,
yeah,
it's
yeah.
0.6.
So like if it was a residential building or something, it'd be
0.4,
0.4.
okay.
Yeah. A hotel or some shit.
Yeah.
And then these values are gonna be this and this. Okay, so what value were we gonna use?
336.
Very good. Oops.
But then that's considering we have to work with two forces, tension and compression.
Yes.
Do we also have to take the negative 68?
So this is if we did the compression design as well, which it says in the question, yeah, but we're not gonna do it
Okay.
because we're focusing on tension. But that's the value we would use if it was for compression.
So,
Yeah.
so the minimum technically you would use for compression.
Yeah.
Yeah. Okay.
But it depends how the question's worded, because sometimes you just get questions where it's telling you that the forces are going in like this, right? So let's see, star. Well, actually, it could just be like G and Q and whatever. But then it says like positive is actually compression, rather than positive being tension. So it's just contextual. Oh, it just popped up now. What I was writing, but yeah, makes sense.
Yeah.
Okay, that's step 1. Step 2. What do we do here? Why are we doing this? Yeah, we'll just start boiling down this formula.
So you have to,
The factor of the
well, you have to compare the ultimate.
Give me a second.
You have to
Oh,
compare
no,
the
we're good.
yielding.
Yeah.
You have to compare the yielding as opposed to the fast fracture one, which is the ultimate failure. So you just do the yielding stress first, the yielding strength first.
Kind of. So we're using a formula that looks similar to the yielding strain one, right?
Yeah.
But it's not the same. So why are we using it?
Wait, what do you mean it's not the same? It looks
Because
pretty similar.
it's that, and then this would be an equal sign.
Oh, because we're trying to make sure that it is less than a certain point.
Yeah, we're trying to ensure that the loading is less than the capacity.
Yeah.
Yeah. So, yes, you're right. Yeah. Okay. It's based on that. Because yeah, fire and all that shit. Okay. The point I'm trying to get at is right. So this is 336 kilonewtons. Let's just do it in newtons, right?
Okay.
Because then we'll have everything else in the same dimensions. This is going to be something, and this is going to be something. So where are we going to get them from?
We're gonna rearrange the equation.
One steel.
Exactly. because we want to find the minimum PFC on one steel,
Okay.
right?
So then you'd use that document AS 4100 and stuff like that.
We use
Um,
Like one steel.
Thing is, right? Let's do one thing at a time because we're gonna have two unknowns, right? So, which one's gonna be harder to get? You reckon?
AG.
Yeah. So, FY, where can we potentially find that?
Data sheet.
Not quite.
AS.
The AS, yeah, the actual
17.
standards.
The standards will just tell you how to use the equations.
Oh, is it?
I mean, it is from standards. You're right, but
Does it
but
say?
what about this particular case?
Stress strain.
Oh, it basically isn't the question.
Yeah.
We're gonna take. So grade 350 is implying that FY is 350. This isn't always the case because it will vary based on thickness, the thickness of your flange and web. But for our initial guess, we're gonna take FY is 350. Okay, so that's gonna be plugged in like that. Okay, so now we basically have to rearrange for AG because that's gonna be a thing that's hard to find. Yeah. My point from earlier. Fuck, my brain is cooked. I'm sorry. This formula is different, mainly because this is 0.9, right? And I know that we said phi is 0.9, but the thing is, this 0.9 will vary based on what type of thing we're designing. So we're designing a tensile member right now, right?
Mhm.
And based on your understanding of compression members, is that going to be a higher or lower number than 0.9?
It's,
If we were designing like the equivalent thing for a compression.
it's gonna be the same, right?
Because of this, yes, but there's another factor to consider which might lower the capacity
Wait, which one?
There's something like where,
for compression.
like how in concrete it's weaker in tension than it is in compression.
So,
But
do you
like
reckon
in
in
steel-
steel it's weaker in tension or compression?
I reckon it's
Compression.
stronger in compression.
So the curve looks like this, right? So it should be the same.
It
But there's
depends
something
on the
that-
structure,
Yes? Why?
buckling failure.
Exactly. Buckling.
Um,
Buckling is a thing that really fucks up compression members for steel.
so it's weaker.
It's essentially weaker. Because most of our steel members are going to have some kind of buckling involved, right? Because it's kind of a small cross section for how long it's going to span, right? And so for compression, this might be something like 0.5. That's my point.
Okay.
Yeah, as an initial guess. But it really depends on like the structure and how long the member is and stuff.
Yeah.
But tension's quite simple because there's no buckling or anything to consider. I'm getting ahead of myself. We'll talk about that next week.
So is concrete and steel like opposite?
To some degree, yeah. So, but the thing is, right, if you have compressive... Sorry, this is talking about steel. I mean, this is talking about reinforced concrete. These are our compression members from before. Compression rear, compressive rear. Can this buckle?
Yes.
No,
Why not?
because the concrete is like capturing it.
Exactly.
Oh.
So buckling only happens in unsupported lengths, like between two floors of a building, for example.
I mean, like, steel can break in compression easily, but concrete can break in tension easily.
Steel, without buckling, has the same strength and tension and compression.
Oh,
But concrete, it breaks very, very easily in tension.
oh.
Yeah.
Okay.
Oh, yeah, that's right. The steel helps the concrete in tension.
Exactly. So we're going to do 350 MPa, and then that's going to give us a number. It's going to give us this, right? If we go to one steel, which I won't for the sake of time, right? What are we going to try to find? We're going to look through our sections. We're going to look at grade 350 section, PFCs. What are we looking for in the table?
Is it the number that's bigger, like according to the standard?
Which number?
Which
AG.
AG, exactly,
Yeah.
right. So it has to be bigger, right? Because if it's smaller,
Then it's not safe.
exactly. So we're going to pick this.
Because
So-
that's, you actually know what that is from one steel.
Yeah, exactly. Because one steel pre-cooked all the numbers
Yeah.
for us, right?
Okay.
That's how we're going to do the questions, basically, for tension.
They're like the standard size of the beams, right?
Yeah, but not just beams, but any member.
Mm.
Yeah, they're this. Yeah, it's like Legos. They're like predetermined sizes for whatever. Okay, so PFC looks like this, yeah, as we mentioned. What part is this? on a PFC?
The center.
The
There's a
web.
word for it. Web, exactly. So TW means the thickness of the web. So of web, sure. And these are the flanges here for a PFC. Right. This is kind of indicating the size. So when we go on one steel, it's going to be called a 125 PFC. And on the table, like across the row, you'll find the gross area. You'll find the thickness of the web, which will be important. Can you predict why it's going to be important later?
Because how thick it is depends on how strong it is, and like it affects the area of.
A little bit, but we already have the area, so why would the thickness matter of the web specifically?
Does it change the area of the flange then? Because if the gross area is fixed, then it has to scale. It has to ratio with the web and the flange.
But all our calculations were to do with, just we have the pre-Beck number for the entire thing, right? So why do we care specifically about TW here?
Because the web makes it skinny and it's gonna collapse.
In what type of failure?
This one.
That's compression though.
Oh wait.
That's the local buckling. But we care about tension, so
Tension. It's gonna yield.
Fast fraction.
yeah, Josh got it.
Ah.
So we're gonna need this for fast fracture. So why?
Oh, because the area.
Cross-sectional area.
The net area.
It's
We're
in
gonna
the
need-
formula.
Yeah, it's in the formula. But I just wanted you guys to think about why. That's all. Pretty much. So FY for this entire course, you're gonna whenever you have anything with a flange and a web, we're gonna take the minimum, right, of the flange and the web's yield strength. Okay. So, why would these differ? So Josh might have the table up. What changes? So it's called grade 350 steel, right?
Yeah, the one.
And then the initial guess I used 350 MPa,
Yeah,
but it's not always 350
Is it
MPa.
because
So
of
why?
the shape of?
Kind of.
because it's like there's stuff for flats and sections, there's things for hexagons.
Oh, that's true. So flats is just any rectangle basically.
Yeah.
So these are both rectangles, the web and the flange. But what do you reckon? Why would they have different yield strengths? I'll tell you, because the yield strength is a function of thickness.
Is it?
Does that make sense?
Is it because they will have fundamentally different thicknesses?
Yeah. The web and the flange have different thicknesses,
Yeah.
and so because of that,
The yield strength.
yeah, the yield strength on the table is different because it's like there's going to be ranges for thicknesses which have certain yield strengths. Anyway, so you have to find both, and you find the minimum because we don't want to be working with two different numbers, right? Because it's going to be super aids, so we just take the worst case.
Mm.
Yeah. Okay, and then same thing on the same table you'll find the ultimate strength as well, and that one's simple. Okay. So first thing we do is we're going to get our area. So which area value are we going to use?
The smaller one.
Are we going to use 1067 or 1520?
1520.
Yeah, why not 1067? That's
Because
smaller, isn't it?
That's too much. That's not actually what you've chosen as your design.
Exactly. That's a preliminary kind of range.
Yeah.
Yeah, it's not a real value. This is the real value we got from one steel, right? And we get 547,000 newtons, but then that's just kilonewtons, right? So that's the whole yield part done. Fast fracture. So how can this fracture based on this arrangement?
The truss arrangement.
Yep. So this was what was in the question for the bolts. It's kind of bolted with it's like diagonal, I guess. 5. It looks like a dice shape. Dice 5. So what were the two failure modes that can happen with this
Yield
pattern?
and fast fracture.
Oh, we're just talking about fast fracture. But what kind of
the
failure modes?
Straight one and
Exactly.
the diagonal thing. The diagonal.
Yep.
failure.
So this is failure mode 1, and then we'll have the staggered and unstaggered holes essentially, right?
Mhm.
Like that. If we look on our diagram, right? So remember the gauge distance is the vertical distance, and the pitch distance is the kind of like horizontal distance that we've moved, or like longitudinal distance. So what, like reading off of here, it's fucking pixelated. Is it? Which one's the gauge distance and which one's the pitch distance?
The gauge distance and the what distance?
The gauge distance and the pitch. The pitch is longitudinal along when tangent's happening, and then gauge is perpendicular to that.
The gauge distance is the vertical.
So what number?
For this it will be. Oh.
So pitch is longitudinal.
Yeah, it'll be.
Gauge
Is that a
is-
right angle? What is it?
So you're doing gauge distance, right?
Yeah. Are they going to be the same as each other?
No. So one will be the 25 and one will be the 30, right?
Oh wait. 25 is the gauge distance.
Yeah, very good. Yeah. So that's
Wait, I don't know what I was looking at. I can't lie.
okay. It's alright. It's fucking 9:30. Yeah, basically, and we're gonna plug those numbers into our formula. Like that. Okay. Here's our formula, right? And that was a sum before in our formula, right? These are sums. But what number are we gonna plug in instead for this? Where the box was.
Is it how many holes there are?
Exactly.
So 2 in this first one.
Yep.
And then for the second one, for the second formula, you do it for 3 holes.
Yes, exactly. And then so SP is gonna be 25, SG is gonna be 30, right? Other way, lol. Yeah. TW we got from what we talked about earlier, right? We can find it from one steel.
4.7.
Exactly. Ooh, yeah, baby.
Let's go.
And so when we do all that, last thing is hole diameter. Okay, so D, and this one's D as well, right? Where can we find that?
Was it in the question?
Kind of. I'll let you, it's like where's Wally? I'll let you find it.
M14 bolts.
Exactly. So what does M14 imply?
T14.
Yeah. So that's 14. But in the code, actually, firstly, what do bolts threads look like?
Threads. What do you mean by threads?
The spirals.
Yeah. They look like.
They're on the inside.
Fuck.
And because they're on the inside,
Yeah.
they're actually getting.
How like what's the difference between this inner diameter
Yeah.
and the outer diameter? Do you reckon of the threads?
Like.
It's called the core and I think the thread diameter.
An
maybe.
actual distance.
Yeah. What do you think roughly that difference
Like
is?
1 or 2.
Yeah. Exactly. So you add on 1 mil on either side.
Oh, and then that.
Yeah. So it's, you just do +2.
Okay.
Whatever M bolt it is,
Yeah.
you just add 2.
That's the design safety.
Oh no, it's just
That's the actual
geometry
thread
of the
pattern.
thread. Because the bolts, yeah, they have that inner core diameter,
And that's 14.
which
and
is
then
that.
Threads is the extra 1.
Yeah,
on
exactly.
each side, which is 2. Okay.
So that's the whole size.
Okay.
Basically, yeah.
So basically, every time you see an M, like.
An M bolt, you add on 2 mil. Exactly.
Okay.
Yeah.
Wait, so the +2 is the spinny stuff.
Yeah, pretty
that's
much.
right.
There's one mil on either side you could consider. Yeah.
Okay.
And it's probably less than that, to be honest. It's probably a bit less, but like because we're doing like kind of worst case scenario, we're subtracting off area, right? Yeah, that's why.
Yeah. Interesting.
Anyway, so that's basically it. So we're gonna do 16 for these, yeah.
So
And
now
then
we have.
and I'll just give you the numbers that we get. So that's that, and this one's this
So you found the minimum and the maximum depending on the 2 parts.
minimum and maximum. Sorry.
Like the highest and the lowest values of like the area.
I wouldn't say highest and lowest areas. It's just different failure modes. So the first one we were doing the straight line area,
Yeah.
and the second one we're doing the diagonal line
Oh,
area,
yeah,
right?
okay. And then you compare the 2 though.
So which one are we actually going to choose?
The smaller one.
Exactly, right? Because we do the minimum of the AN,
Yeah.
the net areas, right? We're going to take that. Oh, sorry. And then we're we essentially just take the small one, yeah. Okay, so
So now that we have that.
that's that. 1369.6. U was 480, right? So not 360. That's the ultimate tensile strength. And do you see this part of the table? KT.
Yeah.
Yep.
For PFC, connect by the web, which is what the detail was on the drawing. The thing is about steels is the details is really hard to read. Like the steel drawings, you're gonna take a while to get familiar with them, because like how steel's connected is really fucking complicated, essentially, right? And so yeah, this is what the cross section of what we're looking at actually looks like, because it's connected by the web or whatever. Anyway, 0.85. Okay, cool. And that gives us 475 kilonewtons. So this was smaller than our previous step, right? Which means it's going to be the value we take, or do you have to take the other one?
We'll take the other. Oh no, take this one.
Exactly. So, since it was smaller and it was on the capacity side, we're going to take it. This value was,
0.9.
and this value was
475, which is
336.
and if it's less, then it works.
Yeah, you can just see from looking at this, it's definitely okay. You can calculate the right hand side if you want, but that's it. That's all we were checking for.
Uh-huh.
And well, it said in the question like find the minimum mass PFC.
Yeah.
So it's like, oh, you can like if you edged it down one more, maybe it would satisfy as well. But this is honestly, it's fine.
Okay.
So it's like it's over by a bit, but not a ridiculous amount. Yeah, and so in an exam condition, you'll probably still get the mark. Okay, any questions? All right, that's a wrap. Thank you.